Okay, so I found this old problem that we're going to go over, and it involves centripetal motion. So I thought it's good to do a couple examples of these. Probably do a couple examples, and then I'm going to do basically an exam 2 review, which will just be questions you might see on an exam, and go through those. But first and foremost, let's do a couple examples where we know what we're doing, and then we'll go back and do some of the pulley questions, exam questions for as well as this. So let's go ahead and get started. It says, in the Gravitron ride at a carnival, people are rotated in a cylindrical walled room. The room radius 4.6 meters, and the rotational frequency is 0.50 revolutions per second when the floor drops out. What is the minimum coefficient of static friction so that people will not slip down? People on this ride say they are pressed against the wall. Is there really an outward force pressing them against the wall? If so, what is the source? If not, what is the proper description of their situation? So I'm going to go ahead and find the minimum coefficient of friction because that's really what's happening. I don't know if you guys have ever seen, I don't know if they're actually called the Gravitron, but basically what's happening is you have a wall, and this goes like in a circle, even though I didn't draw a very good circle. And you stand, I've never actually been on this, but from what I gather, you stand here, and this thing starts spinning like really fast. And once it gets to a certain speed, the floor drops, and you're still suspended. So how does that work? Well, let's work through this really quick. Let's start with a free body diagram of somebody in this situation. We would say they would have their weight force, which we know is mg. We would have a force due to friction holding them up. So if we have a weight force pushing you down, I might be able to find a picture of this. That might be helpful. But if you can imagine being up against this wall with the really big head, you know the force of gravity is pulling you down, but you're stuck to the wall. So there's no net acceleration. So I'm trying to make the vectors the same size. There's also a force of friction holding you up. The normal force is going to be perpendicular. So your normal force is going to be pushing you towards the center. Well, we know that there's going to be centripetal acceleration because this thing is moving. So that's going to be the force causing that. Now, with that in mind, let's do Newton's second law. Now, there's different notations for this. I'm going to call this perpendicular, meaning it's perpendicular to your center. If you were to draw, for example, for center is pointing this way, this is perpendicular. We know that's 0 because they're stuck to the wall. So the force of friction has to equal your weight force, which we said is mg. Well, we know we can rewrite the force of friction as, we know that's just mu naught static times normal equals mg. Or if we go up here, we want to solve for the coefficient of friction. So we know that's mg divided by normal. Turn on my light here. There we go. Now, you might be saying, well, we don't know the normal. And you're right, we don't. So we're going to have to look at Newton's second law to solve that. Now, I'm going to call this centripetal because it's pointing in the direction of our center. So what forces do we have there? Well, we just have our normal force. So our normal force is equal to mass times our centripetal acceleration, which is perfect. But we can rewrite normal in a different way, and that's what I'm going to do. Normal can be written as v squared over r. Why? Because, so I'll just make a note. We're about to do a whole lot of substitution here. Our centripetal acceleration is equal to v squared over r. So I just replaced this with this. Okay, now we can also rewrite this as normal equals m, the radius, which I think is a capital R. They don't give us one. We'll just call it capital R. Squared, omega squared over r. Now, what did we do here? So we can write velocity as your radius times omega. We showed that, I'm pretty sure we've shown all of these in our different videos on centripetal acceleration, which the r's drop. Okay, so we just have normal equals m r omega squared. That's where we're at right now. But again, we can rewrite this. mr times 2 pi over the period, and all this is squared. Why? Because omega equals 2 pi over t. We also don't know omega, we don't know the period either, but we have one more relation we can take advantage of, and that's by saying n equals mr, let's see, 2 squared is 4, pi squared is pi squared, times the frequency. And that's because the period t is equal to 1 over the frequency. So there you have it. That's the normal we're going to want to use and plug into the red. So mg divided by normal mg, and then what's our normal? 4 pi squared mr times the frequency. We don't need to know the mass of the person because that cancels. And our coefficient of friction is g divided by 4 pi squared, the radius times the frequency. And we have all these values. Let's see, gravity is 9.81 divided by 4 pi squared times the radius, was the radius, times 4.6 times the frequency, which was 0.50. So you should get coefficient of friction of about 0.11. And that's all there is to it. So the reason why I did this problem is because I wanted to show you all this stuff in blue. Sure, it's a good problem. It's a somewhat classic problem. I think it's a good problem. But the most important thing I think about this problem, and why professors like it, is because it forces you to know what centripetal acceleration is equal to, what velocity is equal to, what omega is equal to, what your period is equal to get the answer right. I also want to point out, with a lot of these problems, the mass ends up canceling anyways. So if you're working through this problem, you might kind of start to panic because you have normal, which depends on mass, but you don't know the mass of the particular person we're talking about. A lot of times the mass ends up canceling in these situations, so don't over panic. And that's just because of the sum of our forces having the mass in it. That's not going to cancel when we have centripetal acceleration. So the fact that it's not going to be 0, well, you're going to have to divide by m at some point. And obviously, if there's already an m, then that's going to get canceled out. But regardless, the big point is don't freak out if there's m in your equation, you don't know it. and make sure you know these. We did talk about them in the video, and now we kind of applied this to a trickier problem. I'm going to do another problem probably tomorrow on this topic, and then we're going to do a practice exam for, I guess, basically a midterm. So hopefully that was helpful.